Hello everyone, welcome back to Module 2, Session 7, where we were discussing about in the Session 6 about the CMOS. So, continuation of the CMOS here, technologies. We are going for the CMOS advantages, and next moving on to a slightly different concept as a ACR, silicon control rectifier. In the silicon control rectifier, we are going to see about the basic layout and the symbol, two transistor model, and of course the modes of operation of an ACR. In the modes of operation of an ACR, we have namely the forward blocking mode, forward conduction mode, reverse blocking mode. These modes, how it is represented graphically, and how can we identify these modes from the graph, we are going to see in shortly, okay, in the further sessions, in the further PPTs in the same sessions. Now, starting here about the CMOS advantages. Having an introductory session of the CMOS, and we had discussed in the last session how it has been as a why it has been MOS and how it has come with the name as a CMOS, and why the term metal has been given. That all we had seen in the last session. For more knowledge or for refreshing, you can just go back to the previous session and just have a fresh up about the CMOS introductory structure. Knowing the introduction of the CMOS, we are going for the advantages of the CMOS. In the advantages of the CMOS here, first of all, CMOS is complementary metal oxide semiconductor transistors are known for their efficient use of electrical power. They require no electrical current except when they are changing from one state to another. Additionally, the complementary semiconductors work together to limit the output voltage. The result is a low power design that gives off minimal heat. For this reason, CMOS transistors have replaced other previous design such as CCDs in camera sensors and used in most modern processors. If we recall, previously just before CMOS, we just saw MOSFET and FETs, right? And after knowing the advantages of FETs and MOSFET, we were having the comparison in the previous sessions of FET and MOSFET. During the comparison, we have already come across why FET is also called as a square law device. In the same fashion, here, how CMOS transistors are known for their efficient use of electrical power, it can be asked. Okay, and how CMOS transistors have replaced the previous designs, whereas it has been used in the CCDs in cameras or sensors like that. So, why CMOS transistors have replaced other previous design is mainly because of the CMOS technology work together to limit the output voltage. When it is been limiting the output voltage, the result is a low power design that gives off minimum heat. This minimal heat advantage shows off the CMOS structures have replaced other previous designs, and hence it is mostly used in the modern processes. Having this little knowledge of the CMOS technology, we are going further to the ACR. ACR is silicon controlled rectifier. A silicon controlled rectifier is shortly known as SCR. It's a switching device widely used in power control applications. And here it is a 4-layer device, namely P, P, N, P, N, with anode, cathode and gate terminal. SCR, and it's here it is represented symbolically. SCR has a wide range of applications including rectifiers, regulated power supply, DC to AC conversions. If I tell DC to AC conversions, yes, exactly, I am referring to an inverter, a relay control, time delays, circuits and many more to list one. Basic operation and symbols of an ACR is made up of this silicon, as the name has ACR is silicon, because of the high temperature requirement of handling large current and power. Its four layers are PN as shown in this figure. The outer layer P is connected to the anode terminal and outer layer N is connected to the cathode terminal. The P layer is close to the cathode is connected to the gate terminal here. The P layer which is close to the cathode is connected to the gate terminal. The P layer closer to the cathode is connected to the gate terminal here as it is represented. The symbol of an ACR is been here. Okay. Now, when a ACR or when a forward voltage is applied across the anode and the cathode, no conduction takes place as the middle PN junction is reverse biased. Remember, if a positive pulse is applied at the gate, such that the current of this magnitude equal to or more than the gate current will turn on and flows into the current flows into the gate. The current IG will flow into the gate. The ACR turns on and conducts. I repeat here, when a forward voltage is applied across anode and the cathode, then no conduction takes place as the middle layer or this middle PN junction is reverse biased. This is first case. Enhancing this case, if a positive pulse is applied at the gate such that if a positive pulse is applied at the gate means I am applying an IG current, that's it, such that the magnitude is equal to or more than the IG current, then to turn on an ACR, then that IG current flows through through these layers and ACR is turned on and conducts only when IG is greater than or equal. Okay. However, because of regenerative action, removing the gate current does not cause the device to turn off. Still, the ACR will be in on mode. Okay. So this is the two transistor model of an ACR, and the cross-sectional view and equivalent view of the two transistor model of an ACR is represented as follows. Now, cross-sectional view here representation is by splitting these four layers into 3-layer structure like PNP and NPN sandwiched together or attached together the resultant of two circuit model can be obtained. Two transistor model of an SCR can be obtained. So this four layer structure, namely PNPN, is analyzed as NPN transistor and PNP transistor to view the combined model of a two transistor model of an SCR. Okay, the resultant two transistor model is shown here in the equivalent circuit. This is the cross-sectional circuit. Okay, according to this model, the SCR comprises of two transistors, as I told you. Okay, the base of one, that is PNP, and this is NPN transistor. PNP transistor, let it be represented as T1. NPN transistor, let it be represented as T2 for simplicity. The base of PNP is connected to the collector of NPN, and the collector of PNP is connected to the base of NPN transistor. The gate is connected to the base of an NPN transistor. This forms the true transistor model of an SCR. Hope it is clear. Okay. The same thing which I have explained, here it has been written. Okay. The cross-sectional view and the equivalent circuit of two transistor model of SCR is represented as follows. It consists of PNP transistor and an NPN transistor. The base of PNP is connected to the collector of NPN, and the collector of PNP is connected to the base of NPN. This gate is connected to the base of NPN. This is pictorially represented what is being done. I have just told you. Next, working modes of operation of SCR. Working operation or modes of operation of SCR, it's very important and it's very interesting also. Depending on the biasing given to the SCR, the operation of an SCR is divided into three modes. They are forward blocking mode, forward conduction mode, reverse blocking mode. In the forward blocking mode, here, in the forward blocking mode, in this mode of operation, forward blocking mode, the SCR is connected such that the anode terminal is made positive, such that the anode terminal, see here, this is the anode terminal which is made positive with respect to the gate, while the gate terminal kept open. While the gate terminal kept open. Here also you can see anode, cathode and gate. Okay. This happens only in the forward blocking mode. I repeat, in the forward blocking mode, the SCR or the silicon controlled rectifier is connected such that the anode is positive with respect to the cathode. Then while keeping the gate open. Gate terminal, if it is open, then no current will flow. In this state, the SCR is a three junction. Okay, it has three junction, J1, J2, J3, 4-layer device. So in this three junction, the J1 and J3 junctions are forward biased, and the junction J2 is reverse biased. Due to this, a small leakage current flows through the SCR until the voltage applied across the SCR is more than the breakover voltage of it. SCR offers a very high resistance to the current flow. Therefore, SCR acts as an open switch in this mode by blocking forward current flowing through the SCR. This is shown in this characteristics, and hence the name forward blocking mode. This is shown in the VI characteristics. Okay, V means voltage, I means current. Now going on to the forward conduction mode. Okay, see in the forward blocking mode, like this it happens. SCR is connected such that the anode terminal is made positive with respect to cathode terminal, while the gate terminal is kept open. In this state, junction J1 and J3 are forward biased and the junction J2 is reverse biased. Due to the small leakage, current flows through the SCR until the voltage applied across the SCR is more than the breakover voltage of it. SCR offers a very high resistance to the current flow. Hence, in this particular session, mode, the SCR will act as an open switch, and this mode is called as a forward blocking current. Okay, blocking forward current flowing through the SCR, and it is hence known as forward blocking mode. Next, coming to the forward conduction mode. Now we'll see with respect to diagram here. In the forward conduction mode, here in this mode, SCR, the other name for SCR is also called as thyristor. Okay, the SCR comes into the conduction mode, forward conduction mode, from forward blocking mode by two ways. It can be done in two ways. Either by applying a positive pulse to the gate terminal or by increasing the forward voltage. Forward voltage is the voltage between the anode and the cathode. Okay, beyond the breakover voltage of an SCR. Once any one of these methods, I told you these two methods, once any of these methods is applied, the avalanche breakdown occurs at junction J2. Therefore, the SCR turns into the conduction mode and acts as a switch and acts as a closed switch. Whereas in the forward blocking, it was in the open switch. Here in the forward conduction mode, it acts as a closed switch. In the closed switch means the current will start flowing. When the current starts flowing, it is in the conduction mode. Okay, and the current starts flowing through the SCR. In the VI characteristics here, if you see in the VI characteristics here, we see there are different gate currents. IG is gate current, IG is gate current, IG is gate current. IG1, IG2, IG3. These are the three different gate currents. Know that the VI characteristics here, there are different values of the gate current. As and when, if the gate current value is high, the minimum will be the time to come into the conduction mode. See, IG3 is very close, so it will take the minimum time to come into the conduction mode. IG1 is very far, that is more time it will be taken. So IG1 is greater than IG2 is greater than IG3. It means like here, if the gate current value is high, the minimum will be the time for the SCR to come into the gate mode, to the conduction mode. As IG3, IG1, IG2 here when we are comparing, we can see. In this mode here, maximum current will flow through the SCR and the value depends on the current value. Maximum current, it depends on the load resistance or the impedance. Okay. Next, moving on, it is also noted that if the gate current is increasing, the voltage required to turn on the SCR is less if gate biasing is perfect or if the gate biasing is preferred. The current at which the SCR turns on, into the conduction state or the conduction mode from the blocking mode is called as a latching current. So latching current is a current at which the ACR turns into conduction mode from blocking mode. Another current is also available namely as holding current. Also, when the forward current reaches to level at which the ACR returns to blocking state is called as holding current. Hence, these two currents are very much important, like IL and IH, that is latching current and holding current. At this holding current level, the depletion region starts to develop around junction J2. We know that ACR is a 4-layer 3-junction device. So in the middle junction J2, depletion region starts to develop across the junction J2 at this holding current level and this IH current level. Hence, the holding current is slightly less than the latching current. This is an important concept to be noted down. Why holding current is slightly less than the latching current? Okay, here, see, in this diagram, we can see holding current is slightly less than the latching current. Next, another one, last mode of operation is the reverse blocking mode. In the reverse blocking mode, here, in this reverse blocking mode, the cathode is made positive with respect to anode. Understood? Here, in the reverse blocking mode, it is different. The cathode is made positive with respect to the anode. Then what happens is the junction J1 and J2. Here the junction is there J1, J2, J3. Okay. Now this junction, what happens here? These two junctions J1 and J1 and J3 are reverse biased and J2. See, J1 and J3 last are reverse biased and J2 is forward biased, because cathode is made positive with respect to anode in reverse blocking mode. This reverse voltage drives the ACR into the reverse blocking region, resulting in a very less flow of current, or it is also called as small leakage current, which is flowing through the ACR. This small leakage current is not sufficient to turn on the ACR. Hence, ACR acts as an open switch. This all can be seen here in this figure. So, the device offers very high impedance in this mode until the voltage applied is less than the reverse breakdown voltage of a ACR. If the reverse applied voltage is increased beyond VBR, that is reverse blocking voltage, then the avalanche breakdown occurs at junction J1 and J3, which result to increase in the reverse current flow through the ACR. This reverse current causes more losses in the ACR and even to increase the heat of it. So, there will be a less considerable damage to the ACR when the reverse voltage applied is more than the reverse blocking voltage. Okay. Now, this concept clearly shows that the three modes of the operation of an ACR is pictorially represented in this graph and represents like the forward blocking mode, forward conduction and reverse blocking mode. And in the forward blocking mode, we saw that ACR is acting like an open switch because there is a current which is being flowing, but the current is too small to turn on an ACR, and it is an open switch. That is called as a forward leakage current. Whereas in reverse also we saw that a small leakage current is flowing. Hence it is called as a reverse leakage current, and this current is not sufficient to turn on an ACR. Hence again here also ACR will be as a will act as an open switch. Only when it is in the forward conduction mode, ACR acts as a closed switch, and hence the conduction happens only in the forward. The current flows only in the forward conduction mode, and again in forward conduction mode we saw the concept of holding current and latching current, and we saw the relation between the holding current is less than as the latching current and the reason for it. Okay, that's it for now. Hope this ACR concept was very clear. See you in the next session for further concepts on the ACR. Thank you.